Good morning, dear students. In this lecture, we will continue the remaining portion of magnetism and matter. And in this lecture, we have to discuss these topics: magnetic field due to a magnetic dipole, torque and work done on a magnetic dipole, terrestrial magnetism, that is Earth's magnetism, elements of Earth's magnetic field, tangent law of magnetism, and properties of dia, para and ferromagnetic substances. And along with, we will discuss about the diamagnetism, paramagnetism and ferromagnetism in the substances, Curie's law in magnetism and hysteresis in magnetism. To understand the diamagnetism, paramagnetism and ferromagnetism, I will share some other PPT to all of you. So let us start. Magnetic field due to a magnetic dipole or a bar magnet. It is very much analogous to the electric dipole. Let us see. At a point on the axial line of the magnet. The derivation is not frequently asked in examinations, but you can remember formula to solve numerical problems. And the process is very much similar as electric dipole. There is a magnet, north pole and south pole are separated by some distance. Half of the magnetic length is L and total will be L plus L, 2L. There is a point P and it is at a distance x from midpoint of the magnet. Therefore, distance from north pole, magnetic field due to north is Bn, magnetic field due to south is Bs. These two are opposite to each other. Definitely they are opposite in directions. B at P will be resultant of Bn and Bs. And Bp is mu naught upon 4 pi 2m x divided by x square minus L square whole square. Then if L is very less than x, then Bp is approximately mu naught upon 4 pi 2m upon x cube. At a point on the equatorial line of the magnet. What is an equatorial line? A line passing through midpoint of the dipole and perpendicular to the magnetic axis. This OQ is equatorial line. Join the point Q with N and S. Let it makes an angle theta with magnetic axis. Bn is along NQ. Bs is along QS. And the resultant will be along QBQ. That is opposite to the magnetic dipole moment. By isometry, the angle between BQ and BN is theta, and the angle between BQ and BSQ is theta. And you can solve BQ equals to mu naught upon 4 pi m upon y square plus L square raised to power 3 by 2, where y is distance of point Q from midpoint of the dipole. If L is very less, we have BQ in fact, that should be BQ. BQ equals to mu naught upon 4 pi m upon y cube. Magnetic field at a point on the axial line acts along the dipole moment vector, and the magnetic field at a point on the equatorial line acts opposite to the dipole moment vector. Now, the next topic is torque on magnetic dipole. in uniform magnetic field. If a bar magnet is placed in a uniform magnetic field, this uniform magnetic field is represented by blue lines. A bar magnet is there. This bar magnet is placed at any angle with the magnetic field. As you can see, there is a point N, then S is there, force is along this direction, and at N force is along the direction of magnetic field. M is S to N, and there is an angle theta between the magnetic dipole moment vector and magnetic field vector. 2L is the dipole length. The forces on the forces of magnitude MB act opposite to each other, and hence net force acting on the bar magnet due to the external uniform magnetic field is 0. So there is no translational motion of the magnet. But the force acting are along different lines of action and constitute a couple. Hence the magnet will rotate and experience torque. And the torque is magnetic force into perpendicular distance between the magnetic forces. The torque tau equals to mb into 2L sine theta. mb is magnetic force and 2L sine theta is perpendicular distance between the line of action of forces, and that perpendicular distance is from N to this line. And if we take this angle theta, sine theta equals to perpendicular upon hypo. Therefore perpendicular is 2L into sine theta. The perpendicular distance will be 2L sine theta, and torque equals to mb sine theta. It can be represented in vector notation also. Torque vector equals to m vector cross b vector, like this. The direction of torque is perpendicular to the plane containing m and b. That means the torque is perpendicular to this plane of the diagram, is perpendicular and into the plane containing m and b. In this case it is m inside or into the plane, because from right hand Maxwell's rule, if we rotate our bunch of fingers from M to B, the direction will be inwards. Now the work done on a magnetic dipole in uniform magnetic field. This one is the uniform magnetic field. Bar magnet is there. It makes an angle theta with magnetic field. The pole strengths are M is M. Therefore the forces on the ends will be MB along the direction of magnetic field, and MB at south pole opposite to the direction of magnetic field. If it is rotated by some angle and the new position makes an angle theta 2, then in this rotation some work has to be done. How can we find this work? Now the small work done in rotating the dipole is tau d theta, torque into a small angular displacement, and the torque equals to mb sine theta. Therefore dw equals to mb sine theta d theta. Now work done will be integration mb sine theta d theta. If we integrate mb sine theta, there must be some limits also, theta 1 to theta 2, initial position or initial orientation to the final orientation. Now w equals to mb. The integration of sine theta is cos theta, and by taking limits it is minus cos theta. In fact, the integration of sine theta is minus cos theta, and when we take limits it becomes mb within bracket, or you can say minus sign outside, minus mb within bracket cos theta 2 minus cos theta 1. When that minus sign is multiplied, it becomes mb cos theta 1 minus cos theta 2. If potential energy is arbitrarily taken 0 when the dipole is at 90 degree, then potential energy in rotating the dipole and inclining it at an angle theta is potential energy equals to minus mb cos theta, because cos theta 1 is 90 degree, cos theta 1 is 0, and mb within bracket 0 minus cos theta 2, and the orientation theta 2 is theta, therefore minus mb cos theta, or in dot product form it is u at theta equals to minus m dot b. There are some points to be noted. Potential energy can be taken 0 arbitrarily at any position of the dipole. Now, terrestrial magnetism. I would like to discuss some other terms regarding this. Work done on a magnetic dipole in uniform magnetic field. Some more points are required. If it is asked to find out the position of a stable equilibrium, as in case of electric fields, the orientations are very much same. At theta equals to 0 degree, the potential energy of the dipole is minimum, that is minus mb cos 0, and it results as minus m into b. The magnitude is maximum, but due to negative sign, it is minimum potential energy. That means it is the condition of highest stability. Therefore, at theta equals to 0 degree orientation, the bar magnet is in a stable equilibrium, and at theta equals to 90 degree, it is in unstable equilibrium. And work done in rotating dipole from theta 1 equals to 0 degree, from 0 degree to 180 degree is minus, you can put the values, mb cos theta 1 minus cos theta 2. Theta 1 is, cos theta 1 is 0 degree, cos theta 2 is 180. It results as 2 mb. It is maximum work done. Now we can discuss terrestrial magnetism. Terrestrial means it is related to Earth. The terrestrial magnetism is exactly Earth's magnetism. Before starting these terms, Earth behaves like a magnet. Then, is there any magnet inside the Earth? No, there is no any magnet. Initially, it was thought that there may be a huge magnet inside the Earth which causes magnetism in Earth. But with the advancement of techniques and our observations, there is no any magnet or huge magnet placed inside the Earth. In fact, the core of Earth is very hot, and at that high temperature, no magnetic material can show its magnetic property. Then what is the reason for magnetism in Earth? The most probable or the most appropriate reason for Earth's magnetism is, as we know, Earth is rotating about its own axis, so why the core material inside the core is rotating. Due to very high temperature, there may be some ions present inside the core, and if these ions, which are charged one, are moving, that means there is some circulating current, and that current is very strong, and this current is may be responsible, in fact it is responsible for the magnetism of Earth. Some other factors such as radiations, cosmic rays, these are also responsible for magnetism in Earth outside the Earth's surface. Now, the terrestrial magnetism, the basic terms related to this are: geographic axis is a straight line passing through the geographical poles of the Earth. It is the axis of rotation of the Earth. It is also known as polar axis. That means the axis of rotation of Earth is geographical or geographic axis. Geographic meridian at any place is a vertical plane passing through the geographic north and south pole of the Earth. Then geographic equator is a great circle on the surface of the Earth in a plane perpendicular to the geographic axis. All the points on the geographic equator are at equal distance from the geographic pole. Now the magnetic axis is a straight line passing through the magnetic pole of the Earth. It is inclined to geographic axis nearly at an angle of 17 degree. The magnetic meridian, it is at any place, is a vertical plane passing through the magnetic north and south pole of the Earth. Magnetic equator, in a similar way, is a great circle on the surface of the Earth in a plane perpendicular to the magnetic axis, and all the points on the magnetic equator are at equal distance from the magnetic poles. Declination, an important term. There are three basic terms related to Earth's magnetism: declination, inclination, and horizontal and vertical components of Earth's magnetic field. One of them is declination. Suppose this is geographic meridian, this is magnetic meridian, and these two planes are inclined at an angle theta. Then the angle between the magnetic meridian and the geographic meridian at a place is declination at that place. It varies from place to place. Lines shown on the map through the places that have the same declination are called isogonic lines. Lines drawn through the places that have zero declination is called an agonic line. Dip or inclination. This is second important term related to Earth's magnetism. It may be defined as, now you can see, just observe again. There is magnetic field in magnetic meridian. It makes an angle delta with horizontal direction, and the horizontal components of Earth magnetic field is BH, while vertical component is BY. I'm sorry, BV, not BY. BV stands for vertical, H stands for horizontal. The angle between the horizontal component of Earth's magnetic field and the Earth's resultant magnetic field at a place is dip or inclination at that place. It is 0 at the equator and 90 degree at the poles. Lines drawn up on a map through places that have the same dip are called isoclinic lines, and the lines drawn through the places that have zero dip is known as aclinic line. It is the magnetic equator. Now the horizontal component of Earth's magnetic field, The total intensity of the Earth's magnetic field does not lie in any horizontal plane. Instead, it lies along the direction at an angle of dip to the horizontal. The component of Earth's magnetic field along the horizontal at an angle delta, that is dip angle delta, is called horizontal component of Earth's magnetic field, and BH equals to B cos delta. In previous diagram it was there. Similarly, vertical component will be BV equals to B sin delta, such that the square of BH and BV when added and their square root is found, it becomes B, the strength of magnetic field at that place. B is square root BH square plus BV square. Now the tangent law. Suppose there are two fields B1 and B2 at right angles. Their resultant is B. Then this law states, if a magnetic needle is suspended in a region where two uniform magnetic fields are perpendicular to each other, the needle will align itself along the direction of the resultant field of the two fields at an angle theta, such that the tangent of the angle is the ratio of the two fields. That means tan theta equals to B2 upon B1. Tan theta equals to B2 upon B1. Now, comparison of dia, para and ferromagnetic materials. In fact, first of all, we have to at least define what are these dia, para and ferromagnetic substances. The diamagnetic substances, these substances when placed inside a magnetic field, they are repelled by the magnetic field. And the paramagnetic substances, they are attracted by the magnetic field, but they are attracted weakly. And the ferromagnetic substances, they are strongly attracted by the magnetic field. And let us compare these, the properties of dia, para and ferromagnetic materials. There are so many points in the comparison. The first point, the diamagnetic substances are those substances which are feebly repelled by a magnet, and the examples are antimony, bismuth, copper, gold, silver, quartz, and so many are there. Paramagnetic, again, the substances are those substances which are feebly attracted by the magnet and they are strongly, ferromagnetic materials are strongly attracted. Second point, when placed in magnetic field, the lines of force tend to avoid the substance. In case of diamagnetic substances, the magnetic field lines will not pass through the material. In paramagnetic, they will pass through the material, and in ferromagnetic, they will strongly pass. Suppose paramagnetic material is ferromagnetic is there. Now you can see the lines, magnetic field lines are not going into the material. In case of paramagnetic, the lines are going into the material. In case of ferromagnetic, now the extent of magnetic field lines which are going inside the material is more in ferromagnetic and less in paramagnetic. Some other points are there. When placed in a non-uniform magnetic field, it moves from a stronger to weaker field. Due to repulsive nature, in diamagnetic substances, when they are placed in a non-uniform magnetic field, they will move from a stronger field to weaker field. That means they have a tendency to get away from the field. And for paramagnetic substances, it moves from weaker to stronger. And for ferromagnetic, it moves from weaker to stronger field and have some strong attraction. In case of paramagnetic, there is a weak attraction. When a diamagnetic rod is freely suspended in a uniform magnetic field, it aligns itself in a direction perpendicular to the field. In case of paramagnetic, it is parallel to the field. You can see here it aligns parallel to the field. And in case of ferromagnetic, alignment is again parallel, but comparing with paramagnetic, it align fast. Yes, you can see here it aligns rapidly. Now next point of difference, a diamagnetic liquid taken in a watch glass is placed in uniform magnetic field. It collects away from the center when the magnetic poles are closer and collects at the center when the magnetic poles are farther. Again, the concept is very much clear. The substance has a tendency to move from stronger field to weaker field, like this. And in case of paramagnetic substances, they will the material will flow towards stronger fields. Similar is the case with ferromagnetic substances. Now when a diamagnetic substance is placed in a magnetic field, it is weakly magnetized in the direction opposite to the induced field. That means the magnetic induction is there, but it is opposite to the magnetizing field. In paramagnetic substances, it is along the direction of magnetic field, but it remains only when there is a magnetizing field. If we remove magnetizing field, no magnetism will be there. In case of ferromagnetic substances, if it is placed in a magnetic field, it is strongly magnetized in the direction of the inducing field. Now the induced dipole moment is small in case of diamagnetic substances and negative also. In case of paramagnetic, the induced dipole moment is small and positive. In case of ferromagnetic substance, the induced dipole moment is large and positive. Now intensity of magnetization has a small and negative value, and intensity of magnetization for paramagnetic substances, it is small and positive. For ferromagnetic substances, large and positive. Now the magnetic permeability for diamagnetic substances, it is less than unity, that means less than 1. For paramagnetic substances, it is more than 1, and for ferromagnetic substances, mu is large, that is much more than 1. Then magnetic susceptibility, chi, it has a small negative value for diamagnetic substance. Susceptibility is positive and is small for paramagnetic, and it is large and positive for ferromagnetic substances. Now the diamagnetic substances, they do not obey Curie's law. We will discuss it later on, what is Curie's law. That is, their properties do not depend with, or their properties do not change with temperature. They obey Curie's law. The paramagnetic substances, they obey Curie's law. They lost their magnetic property with rise in temperature. And they obey Curie's law in ferromagnetic substances. They obey Curie's law at a certain temperature called Curie point. They lose ferromagnetic properties and behaves like paramagnetic substances. Now what is Curie law? The magnetic susceptibility of a material varies inversely with the absolute temperature. I is the magnetic susceptibility is inversely proportional to T, or I is directly proportional to H upon T. And chi is directly proportional to 1 by T. The Cm is chi susceptibility. Cm equals to C upon T, where C is C is known as Curie constant. Curie temperature for iron is 1000 Kelvin, and for cobalt it is 1400 Kelvin, and for nickel it is 600 Kelvin. That means these ferromagnetic substances behave like paramagnetic substances respectively at 1000 Kelvin, 1400 Kelvin and 600 Kelvin. And if we plot I with respect to H upon T, the curve is like this. Hysteresis loop or magnetization curve. What is magnetization curve exactly? If suppose we have a magnetizing field, a magnetic sample is there. When we change magnetizing field, the magnetization occurs in the magnetic sample. Suppose this is H axis, that is magnetizing field axis. This is intensity of magnetization axis. O is origin. If we increase magnetic field from 0 to higher values in positive direction, then the magnetization will increase as shown by the blue graph line. If the field is decreased, when the magnetizing field becomes 0, some intensity of magnetization, or you can say some magnetization, still remains in the sample. To make it 0, the magnetizing field should be reversed, and at this point the magnetization is 0 and magnetizing field is have some negative value. And if we increase the magnetizing field in reverse direction, the magnetization increases in opposite direction. And after that, when we increase the magnetizing field, the intensity of magnetization keeps on decreasing. At this point E, the magnetizing field is 0, but still magnetization remains in the sample. To make it 0, we have to increase magnetic field or intensity of magnetizing intensity up to this point F. This closed loop is known as hysteresis loop. The meaning of hysteresis is lagging behind. That means कि पीछे रह जाना. अब क्या पीछे हो रहा है देखिए. H आपने डिक्रीज करना स्टार्ट किया. H तो 0 हो गया, बट इंटेंसिटी ऑफ मैग्नेटाइजेशन अभी भी 0 नहीं हुआ. देयर इज अ लैगिंग इन इंटेंसिटी ऑफ मैग्नेटाइजेशन, एंड दैट लैगिंग LAGGING लैगिंग, पीछे रह जाना, is known as hysteresis. Intensity of magnetization increases with increase in magnetizing force initially through OA and reaches saturation at A. When H is decreased, I decreases, but it does not come to 0 at H equals to 0. The residual magnetism, that is remaining magnetism I, set up in the material represented by OB is called retentivity. You can understand it. जब H की वैल्यू 0 हो गई, तब इंटेंसिटी ऑफ मैग्नेटाइजेशन की अभी भी पॉजिटिव वैल्यूज़ हैं जो कि OB के इक्वल है. दिस OB इज़ नोन एज retentivity. To bring I to 0, that is to demagnetize completely, opposite or negative magnetizing force is applied. This magnetizing force, in fact the magnetizing field represented by OC, is called coercivity. After reaching the saturation level D, When the magnetizing force is reversed, the curve closes to the point A, completing a cycle. The loop A, B, C, D, E, F, A is called hysteresis loop. The area of the loop gives the loss of energy due to the cycle of magnetization and demagnetization and is dissipated in form of heat. ये एरिया जितना पतला होगा उतना ही हिस्टेरेसिस लॉस कम होगा, और अगर ये एरिया ज़्यादा होगा तो मैग्नेटाइजेशन और डीमैग्नेटाइजेशन के प्रोसेस में एनर्जी लॉस ज़्यादा होगा. The material like iron having thin loop is used for making temporary magnets, and that with thick loop like steel is used for permanent magnet. That means कि अगर आपको आर्टिफिशियल या इलेक्ट्रोमैग्नेट बनाना हो तो आप आयरन का यूज़ करेंगे ताकि मैग्नेटाइजेशन और डीमैग्नेटाइजेशन में एनर्जी लॉसेस कम से कम हो, और अगर आपको परमानेंट मैग्नेट्स बनाने हैं तब आप स्टील का यूज़ कर सकते हैं. आप देख सकते हैं हिस्टेरेसिस लूप के साइज़ को, एरिया को इनफैक्ट कम और ज़्यादा किया जा रहा है. तो जो कम एरिया होगा उसमें हिस्टेरेसिस लॉसेस कम होंगे और ज़्यादा एरिया में हिस्टेरेसिस लॉसेस ज़्यादा होंगे. This is end of the magnetization, and in fact I will suggest all of you परमानेंट मैग्नेट्स और इलेक्ट्रोमैग्नेट्स के लिए और किन किन डिवाइसेस में ये यूज़ किए जाते हैं आप एनसीईआरटी की बुक में ज़रूर इसको स्टडी करें. मैं उसके स्क्रीनशॉट्स आपको भेज दूंगा. आई होप कि आपको लेक्चर समझ में आया होगा. कोई भी डाउट्स हो आप पूछ सकते हैं. थैंक यू सो मच.